Hi, today we will discuss our first type, which is type of electrical transient, which is the RL series circuit, but this is in terms of DC source. Okay, now the question is just a little bit of a preview why there is transients. Okay, so there is a transient because of the energy storage elements. So as you can recall on your undergrad, so we will discuss that when we have that lesson, that the energy stored, okay, by an inductor, I could say L is inductor, C is capacitor, L is inductance, is 1/2 Li squared. Okay, and the energy stored of a capacitor is 1/2, okay, capacitor voltage squared. So the energy of the capacitor is dependent on voltage, the energy of the inductor is dependent on current. So it means that if you have those elements connected in a circuit, there's an energy storage. If that is only resistor, if you have a switch, if you open and close the switch, the current is 0. The current has a value if that is closed. So that's why one of the application of transient is on switching. There are plenty of switching transients or application of transients, but that is the typical one in terms of switching, when you open or close a switch. And there's no one in the world who see a current, even formulated an equation just to get current. So again, the current here is, you cannot see that one, but we can compute. Okay, let's go forward to the discussion proper of an RL transient or RL series circuit for transient. So you have here a voltage E, and you have a combination of R and L in series. Now you have here a switch, and there is an initial condition which is we need to remember, because when we derive the formulas, it is very important, okay, in getting the characteristic solution later. So at time is equal to 0, the switch will open, and thus the current will be 0 in an open condition. However, if you have the KVL around the loop, we have here the voltage at the resistor, the voltage at the capacitor, okay, voltage at the inductor EL. If you have the KVL around the loop and we use the first in method, so you have plus minus here, the drop plus minus, it will yield with this equation here that the total battery voltage will be equal to ER plus EL. But ER, or the voltage at the resistor, is I times R, and also this one thing as well, EL is equal to L differential of the current. So EL is equal to L di all over dt, and it will become equal to E when the switch opens. So it means, since we do not see current, it will depend on the differential of the current. So it is not necessary that EL is 0. Okay, just recall this equation number 1, that EL is L di dt and ER is I times R. But if the switch opens in a resistor, the current is 0. So ER is 0 here. So therefore, that the total voltage E is equal to L di dt, or simply equal to EL. Okay, that is if the switch will open. Now, if eventually the switch will close, so I is equal to R, ER, I times R, and EL, L di dt. And from equation number 1, we can substitute those values here. The main thing here is we need to get, our main goal is to get that I. That I is your so-called transient current. Okay, transient current I, capital letter I. Okay, so this, that is the, which is dependent on constants, which is R, E, and L, which is the given on the problem. So how we will do that? We will make use of differential equations later. So L di all over dt plus I times R equal to E. Now, to continue it, so from our last slide, we stop here. That we need to get the transient current dependent on constants R, E, and L, or resistance, the voltage and total voltage E, and L, which is the inductor. So for this, we have this equation here from the last slide, and we can still simplify this further. So it will become negative IR plus E, and then simplify it further so that we can have a much better integration later. So we have the common here as resistor R, and then I minus E all over R. So if you do this one, it will become like this. We just change the form. Okay, now since we already have this one and the LDI dt, so we can have the differential in terms of current, we can have the constant in terms of time. So time will come, we'll have at the right side of the equation, and then this I minus E all over R at the denominator of di, and then integrate both sides. So if we do that, we have this equation here. Now we can simplify this further by integration. The result will be this one, ln of I minus E all over R, because di all over I minus E all over R, when you integrate it, it will become ln U, is equal to negative RL times T plus K. And then this equation must be multiplied by E, so that it can simplify further. Ln E is equal to 1, and then E will raise this expression here, negative R over L times T plus K. Now, how can we simplify this further? So, to simplify this further, we need to have the identity of this. So, if you can still recall, the identity of E x times y, or raised to x times y, is equal to EX. Okay? EY. Okay? So, x plus y rather is simply EX times EY. So, that identity here will become like this. Okay? So, from this one, it will become like this. So, e to the k, I could say that is constant A, and then I minus E all over R. Now, the question is, how can we get that constant A? So, we go to the initial conditions of the problem. Having I is equal to 0 and time is equal to 0 to get the complementary solution. And then, it will become like this, no? I is 0. T here is equal to 0. So, e to the 0 is equal to 1. So, A is equal to E is equal to negative E all over R, which is, I could say, equation 3. Now, equation 3 can be substitute here at equation number 2, and we can now solve for transient I. Okay, the final equation for transient I is simply equal to this. A very, very important equation. E all over R, 1 minus E raised to negative RL over T. Okay, RL all over T. R over L times T. Okay, now what's the meaning of this when you say transient? Of course, if you have a switch, the signal will become like this, and then after some time, if the switch closes, it will become steady state. Now, this is the equivalent graph curve of that transient current versus time. And you have here the transient behavior and the steady state behavior. The steady state behavior is basically is E all over R, because that's the steady state condition. And this multiplier here, which is 1 minus E raised to negative R all over R times T, is the effect of the transient. So it will transient first and then it will become steady state. Now we will discuss the other formulas on the next slide. Okay, good day to all of you. Now we will finalize the important formulas for DCRL transient series circuit. What we have discussed from the last slide, we derive the transient current, which is based on constants. So the constants here are your resistance, your total battery voltage or your input voltage at DC, and your inductor L. So we will establish this transient current as equal to E all over R multiplied by 1 minus E raised to negative R all over L times T. Now if you want to get the voltage at the resistor, just apply Ohm's law. So ER is equal to I times R, and then R will cancel out. And hence, this formula is almost the same, but without the R. You divide it by R. So, or the R will cancel out. So, this will be the formula for ER, E times 1 minus E raised to negative R over L times T. Now, if you want to get the voltage at the inductor, so we have this equation from our previous slides that the inductor voltage is equal to L di times dt. So from here, we need to differentiate this current in order to get EL. So what will happen is this. Okay, EL is equal to L times the differential of your I, which is this term here. Okay, just do the differential the calculus here, and what will happen, it will arrive at this final equation. So do the calculus here. So differential calculus, so it will become E times E here is the battery voltage times E raised to negative R all over L times T. Okay, these three formulas are the most important formulas for the DCRL series transient. So typically on the board examination, it is always DCRL or DCRC series. But these formulas here are the most important formulas for the RL series combination. Okay, one more thing that we need to discuss is the time constant. So, what is time constant? That is the time it takes for the exponent E to become a unity, or on other words, that is the time it takes for the transient current I, for this example, to become 63.21% of the steady state value. So, these time constants are for RL and RC series circuits. Okay, the question is, how did we arrive at this time constant at RL? TC is time constant as an abbreviation. Okay, what we will do is go back to this equation of the transient current I. Okay, if we consider time is equal to 0, so what will happen here, or rather time is equal to 1 second, by the way, 1 second. So it will become like this, E all over R, 1 minus E, negative R all over L only. Okay, because the T becomes unity. So this is R all over L. And this is 1. Okay, now the time constant is the time wherein the exponent E here will become unity. Of course, we use 1 second as our time at the x-axis here. So, to become unity of this exponent, we need to multiply a constant. which is the time constant. So if you multiply this by L all over R, it will become E raised to negative 1, okay, exponent. So it become unity. So this, okay, negative 1. Okay, so the time constant is L all over R simply because we make use of L all over R to be multiplied to the negative exponent of E to become unity. Okay, if this will be the case, okay, is the remainder of that equation, and we already know, okay, that E all over R, okay, from the previous slide is the steady state behavior. So if you manipulate this equation here, that is simply 0.63212 to be exact, or 63.21% of the steady state. So that's why it is the so-called time constant. So that the exponent E will become negative 1, and that will be the 63.21% of the transient, okay, curve to become unity. Or simply, if you draw that, okay, in a graph, okay, this is the steady state, that is E all over R, this is the current, and this is the time. Okay, this is the 63.21% of time is equal to 1 second. So after 63.21%, the signal will become steady state behavior, or DC. Okay, we will discuss on the next slide the DC RC transient series circuit. Good day to all of you. Now, we will continue our discussion on our second part of the DC circuit series, or DC transient series circuit. Now, the first DC transient series circuit that we discussed is the RL series circuit. Now, today we will focus ourselves now to DC RC series circuit. When I say RC, resistor and a capacitor in series. Okay, now we need to have again a switch here so that there is a transient. So we have here a transient current I, small letter I. Then the battery voltage E, resistor R, and a capacitor C. The resistor and the capacitor has its corresponding voltage ER and EC respectively. Okay, our constants here is R, E, and C. Okay, from our last meeting, last slide rather, is R, E, and L. Okay, our initial conditions now will be changed. At time equal to 0, the switch will close, and the capacitor has no initial charge. So it means Q will become 0 at this condition. Okay, by KVL, no, by using again polarity max, so this will become the drop, voltage rise. So ER plus EC is equal to E using the first in method by the KVL. So it's very evident here in the circuit. Now we can recall some important equations. So this is from your physics. So I forgot to enclose it on a box. That the capacitor voltage E is simply equal to the charge all over capacitance. And of course, the current I is the differential of the charge with respect to time, or dq all over dt. Okay, now if this is ER, that is I times R, then EC is Q all over C, simply equal to the battery voltage E from equation number 1. Okay, all we have to do is to substitute the current I here by dq over dt, yes, okay, and QC is equal to EC equal to E. What will happen here is we need to rearrange the equation so that when we integrate, we have the same variables. Okay, we have R dq over dt equal to negative Q all over C plus E. We can arrange this one, no, by having the common of the term here, which is 1 all over C. So this is the same here. So the main thing here, why we need to arrange it, so that dq will in terms of Q and dt is in terms of a constant. Please take note that RC is the constants here, okay, of the circuit, and then E. Okay, without further ado, dq all over q minus ce, 1 negative r all over c. And then dt will go to the right side of the left side of your equation. And then we need to integrate so that we can eliminate the differential. Okay, for this is du over u, ln u, okay, ln q minus c, then equal to, okay, the constant t all over rc plus k raised to e. Rather, we need to multiply this by ln e, by e rather, so that we can further simplify this equation. So ln e is equal to 1, and then we raise e by negative t over rc plus e raised to the k equal to q minus ce. Now, we will conclude the formulas for the DC-RC series circuit on transients. So we stop on the last slide here. So we have this equation here, q minus ce is equal to e raised to negative t all over rc times e raised to the k. So this is the same thing with what we have discussed on our RL series circuit. Okay, we're using this identity here or property for the exponential e. Okay, now a little bit of simplification, and we can have e raised to the k here as a constant a. So we need to get a here from the initial condition, so we need to get the complementary solution. So in this case, we go back to the initial condition that when the switch is closed, q is equal to 0, switch is closed, q is 0, and time is equal to 0. So substitute here at equation number 2. It will yield to this answer here that a is equal to negative c times e. So this is negative c times e. So this is equation number 3 now. Substitute equation number 3 here to equation number 2, then simplify things. It will yield to another important equation in terms of charge. So the charge is equal to CE multiplied by 1 minus E negative T all over RC. So this is negative T over RC. So we already solve the charge here, okay, with respect to time. Okay, this equation. So we need the transient current. So what you will do is go back to our equation a while ago that the I is differential of Q all over dt. Differentiate with respect to time this equation here and use differential calculus. And that way, we will have the answer for the transient current equal to E all over R, E raised to negative T all over RC. Okay, we can now get the other parameters like voltage across the resistor ER, which is from Ohm's law, I times R. So just multiply the current I by R, then it will cancel R here, and then it will yield with this equation, E multiplied by E raised to negative T all over RC. This is raised, okay, raised to T all over RC, negative T all over RC. And then we can now get the voltage across the capacitor by having Q all over C. So what you will do is to divide this equation here by C. Q all over C is obviously EC. So C will cancel out, and then it will arrive at this equation here. So this is the capacitor voltage equal to E multiplied by 1 minus E raised to negative T all over RC in terms of volts. And last but not the least, the time constant. So the time constant is R times C. So because if we multiply RC here at this exponent E, and we have time is equal to 1 second, for example, it will become a negative exponent, negative unity exponent. So all of these formulas are very, very important for the applications on DC-RC transient series circuit. So we will discuss the double transient on the next slide, which is the RLC series circuit. Hi, let's move forward to our last case for the DC transient series circuit. So this is a DC RLC transient series circuit. So as the name implies, we have two energy storage elements here. which is being placed simultaneously, which is L and C respectively. So we have again a switch here, and then the current I, and then your battery voltage E, and then the RLC parameters with the corresponding voltage ER, EL, and EC respectively. So this is also called a double transient because you have L and C now, which being placed in series with the resistor. Okay, the initial conditions, we have time is equal to 0, the switch is closed, I is equal to Q, or the charge is equal to 0. Okay, I will not go to the deeper math here, simply because what is very important when you're taking the licensure exam is not the derivation, but we need the derivation, of course, to fully understand the principle. But in this case, since we do not need to compute the eigenvalues and then get the roots, so instead, this type of problems for DC RLC series circuits is more on determining the type of case, or the characteristic cases. Okay, we have 4 type of cases for a DC RLC series circuit. You have the undamped, the overdamped, the critically damped, and underdamped, which is dependent on the RLC parameters and how you will evaluate them. Okay, let's go to case number 1. Case number 1 is the so-called lossless circuit, and it is undamped circuit. Now, based from the title itself, lossless circuit, you have resistance simply null or 0. Okay, that is case number 1. Now, let's move forward to case number 2, which is an overdamped case. We have this characteristic case equation, which is R all over 2L raised to squared 1 all over LC. So, it's dependent if that's greater than, equal, or less than. Now, let's go to the shortcuts. If that is less than, it means that is greater than, rather. That is greater than, sorry. If that is greater than, that is over damped. So, if that is less than, that is under damped case. And last but not the least, if that is equal, that is critically damped case circuit. So please do recall all of these equations here, which is the characteristic test equations, which is very important. And we will not go to the details of getting the roots of the equations. But I have a separate discussion for this one on double transient on the next episode or next lessons. So stand by for that. And we will now solve some problems on DC series transient circuits. Thank you at maraming salamat.